Hello everyone, welcome to the course Remote Sensing Principles and Applications, and in today's lecture we are going to continue with the properties of EMR. In the last class we discussed two important properties of electromagnetic radiation. One is polarization, which indicates the orientation of the electric field within the electromagnetic radiation. So, based on the orientation of electric field with respect to the plane of incidence, we can classify the polarization as horizontal, vertical or even circular. I also explained you that based on the polarization, the amount of incoming energy will vary, that is the total energy coming in will be having different polarizations, and by limiting our view either in like any one type of polarization will actually limit the total energy that is reaching us. And it has like major implications in how objects interact with EMR, especially in the microwave regions. In microwave regions, when we do remote sensing, we will be more interested about understanding the polarization behavior of the materials also. So, the next important property of electromagnetic radiation that we looked upon is coherent radiation. So, coherency is defined as whether the electromagnetic radiation has a systematic phase relationship between them. When two waves are progressing, if they have a systematic relationship between them, we call them as coherent or non-coherent based on that. So, if two waves are coherent, then and if they are superimposed on top of each other, they will produce interference, that is their amplitudes will add up, and if those two coherent waves are in phase, the amplitude of the resultant wave will be higher than the amplitude of the individual wave components. This we call constructive interference, that is the amplitude will increase, we call it as constructive interference. On the other hand, if the amplitude of the resultant wave decreases after the superimposition of two waves, we call it as destructive interference. Destructive interference will happen when the two waves that are meeting together are out of phase or like not in phase with each other. So, they will be kind of cancelling out each other when they add up. Today we are going to continue on seeing different properties of electromagnetic radiation. One of the major change that will happen when electromagnetic radiation travels from one medium to another medium. Here medium I mean is like whether it is travelling through air or travelling through vacuum or travelling through some other materials like water and so on. So, the medium through which electromagnetic radiation travels will influence the velocity of the electromagnetic radiation. That is, when the medium's density increases, naturally it is the velocity of electromagnetic radiation while travelling within that particular denser medium will lower. Actually, that is given here in this slide, that is here I denoted as Cm, where Cm is the velocity of electromagnetic radiation in the particular medium, say for example water or air whatever, and C is the velocity of electromagnetic radiation in vacuum. So, we all know that C roughly equals to 3 into 10 power 8 meter per second, and when it travels through another medium depends on the medium's refractive index. So, refractive index is you can think it of as like how much the light ray will bend or how much the medium will bend the light ray when travelling to it, it is roughly the refractive index. So, based on the refractive index of the medium, the velocity will change correspondingly. That is, if the refractive index of medium is higher than the refractive index of vacuum, then the velocity in the medium will go down. Say the velocity in air is, or the refractive index in air is roughly about 1.003 or something, and for water it will be around like 1.1, 1.2 something of that sort, and refractive index of vacuum is 1. So, if you substitute in this equation, we can observe that the velocity of EMR travelling through water or air is less than the velocity of EMR in vacuum. So, we also know the relationship that C is equal to nu lambda. So, when velocity changes, this relationship will change. So, how it will change? The wavelength of the medium will change, but the frequency will be preserved. That is, when EMR travels between one medium to another medium, the wavelength will change according to the change in velocity On the other hand, the frequency will remain more or less constant, not more or less, it will remain constant, it will not change. Also, when EMR travels from one medium to another medium, it will undergo different processes. Different processes means like on the interface of the two mediums, like as given in this particular slide. Like this is medium 1, this is medium 2, and this is the interface between the two mediums, some surface there, say between air and a water body. Let us say there is a water body, air is standing above it, EMR is travelling from air to water. When EMR is incident, it will be first thing partially reflected. Reflected is it will be like reflected back as if like a mirror reflects. Any objects will have some reflectance and it will reflect the EMR in any direction. And also if the object is transparent or translucent, then the EMR will penetrate that particular second medium, and by virtue of difference in refractive indices, the EMR will undergo what is known as refraction. So, two things will happen when EMR travels from one medium to another medium. Like first thing I said, velocity will change, that is one thing. Second thing is, from the surface that acts as interface between the two mediums, part of incoming radiation will be reflected back. Similarly, some portion of EMR will penetrate through the medium, second medium, and while penetrating it, if the refractive indices between the two mediums are different, then the path in which the light ray travelled will differ, will vary. Say the incident ray here in this light travel in this particular direction, by virtue of difference in the refractive indices of medium 2, it actually encountered a slight bend, like its direction will change. So, the EMR will undergo reflection as well as refraction. If the surface is like smooth, like the surface acting as the interface between the two mediums is smooth, and also the mediums are non-lossy. Non-lossy in the sense energy coming in is like preserved while passing through the medium, then what will happen is they will obey what is known as a Snell's law. That is, if the surface between the two medium is perfectly smooth, the EMR will obey Snell's law. That is, the angle of reflection or the angle of incidence will be equal to the angle of reflection. Say here the angles we are measuring with respect to the normal to the surface. This is the surface separating the two mediums, this is the normal to the surface, and we are measuring the angle with respect to the normal. So, the angle with which EMR is reflected will be equal to the angle at which it was first incident on the surface. This will be obeyed if the surface is perfectly smooth. Also, this in relation to refraction, this law also will be obeyed. That is, n1 sin theta I is equal to n2 sin theta r, where n1 and n2 are the refractive indices of the two mediums. Theta I is angle of incidence, theta r here is, I write it here, reflection, theta r here is refraction, angle of refraction, like how much the ray is bent actually. What is the implication of this refraction of EMR? Actually our atmosphere, we all know it consists of multiple layers, like different layers have different constituents at various temperatures at different densities, and hence the refractive indices also will vary. So, there are several layers within the atmosphere, and also after travelling through atmosphere, the EMR will reach the earth surface. So, while travelling through atmosphere and also when reaching the earth surface, EMR will undergo refraction several times by passing through mediums with different refractive indices. If the medium, say medium 2 has a higher refractive index than medium 1, then light ray will be bent towards the normal. Or on the other hand, if medium 2 has lower refractive index, light ray will be bent away from the normal. Like this, light ray will be travelling in different directions when it travels through mediums with different refractive indices. While discussing reflection refraction, I said we are not going to care about the energy loss. We assume two mediums through which EMR is passing through is lossless, non-lossy medium. But most of the mediums through which EMR passes on the earth surface is actually lossy. Lossy in the sense when some units of energy enters one medium, and when it emerges out of the medium after passing through, the energy will be reduced by certain factor. We call such mediums in which energy is lost actually or lossy mediums. Atmosphere, earth surface features, almost everything are lossy medium. When EMR interacts with them, some part of EMR will be lost from it. So, how this actually happens, why EMR is actually lost? EMR, the energy is lost primarily due to two processes. One is known as scattering and another one is known as absorption. So, absorption, we all know, like whenever some energy is incident on it, the materials or the molecules inside the materials will be using up that energy to do some work, like the molecules will undergo some sort of rotation or orientation change, or they may heat up increasing the temperature of object, anything can happen. So, that particular energy which is incident on object is actually used up by the molecules within the object. This is known as absorption. On the other hand, scattering means the incoming energy, rather than being passed as such, will be split up into different directions. Like a simple example I will give in this slide. Say when energy is coming like this in this particular direction and some medium is there, let us say the medium is full of some sort of molecules. So, when it is incident on it, if it is a lossy medium, then some portion of it will be absorbed, that is used up by the molecules within the medium, and some portions will be scattered in different directions. So, what essentially happen, let us assume like 10 units of energy is coming in, some random units or some I am assigning just for explanation sake. So, when some observer is like waiting here to receive the energy, like some sensor is placed here to receive the energy, and this electromagnetic radiation will is passing through this medium. When it comes out of it, let us say like 2 units is absorbed. So, we will be expecting 8 units here, but that 8 units also will be now scattered in different directions. Now, it will be reflected in multiple directions, maybe leaving only 1 or 2 units coming out in this particular direction. So, the sensor will receive actually much lesser energy than what is anticipated. So, essentially absorption is the energy being used up by the object itself or the medium itself, whereas scattering, the incoming energy in one particular direction is now split into several directions. Hence, that particular energy is lost in the direction in which we are expecting it. If we keep a sensor on the other side and waiting to measure the energy, we will be receiving much less energy than what is anticipated. This is scattering. So, actually there are very simple relationships between the incoming energy and what is being like coming out, how much is the absorption taking in. Normally in remote sensing, we will not be looking at scattering separately, absorption separately, like whenever energy is lost, it will be due to both these components together. If we take both these components together, we call them as attenuation or extinction. So, what is attenuation or extinction? That is the total amount of energy that is lost. So, there is like a general small equation relating the power incident on an object and the power that has been coming out of an object. That maybe I will go back and explain in this slide. Yes. So, the equation will take a form of this, where E naught is the power incident on the particular medium, Z is the distance travelled within the medium, and Ez is the power of the EMR that is actually present after travelling through the medium. That is the say this is like a medium, EMR is coming in like this, it travels a distance of Z and it is emerging out here. So, here we measure the incoming power as E naught, here the power is Ez. So, this relationship Ez is equal to E naught e power minus k Az is the simple equation relating the incoming power with the emerging power after it travelled through certain distance in the medium, where Ka is what we call as absorption coefficient. So, whenever an object enters through a medium, there will be some loss, and that particular equation is given by E naught is equal to E is equal to E naught power exponential of minus Ka Z. where Ka is called absorption coefficient if we consider only absorption. It will be called scattering coefficient only if we consider scattering, or if we consider both of them together it will be called attenuation coefficient. For us to understand attenuation coefficient first we will understand what is known as a penetration depth. Okay. So, a penetration depth or absorption depth, whatever we can call, is defined as the particular distance through which EMR has to travel within a medium such that the final power will be 1 E of the power that entered into the medium. That is, like I give you the same example I gave, like this is one particular medium, EMR is entering through this particular direction with a power of E naught, the total length of the medium is Z, the power we receive out is Ez. So, if Ez is equal to 1 by E times of E naught, then we call Z as absorption length or penetration depth, whatever. If this is like depth, we call it as penetration depth, or we call it as absorption length in generally. That is, the power that is entering a medium will become 1 E of the power that is emerging out. Okay. So, this is called penetration depth or absorption length. So, the coefficient, either the absorption coefficient or attenuation coefficient, by considering whatever processes we take into account, that is defined as 1 over this penetration depth, that is whatever coefficient we consider. If we consider everything together, absorption coefficient is 1 over penetration depth due to absorption, or scattering coefficient is equal to 1 over the penetration depth just due to scattering, or if we take both of them together we call it as extinction coefficient, that will be 1 over the total length accounting both scattering and absorption. So, that is given in this particular slide, like the extinction coefficient is equal to absorption coefficient plus scattering coefficient, and the attenuation length is equal to 1 by LE is equal to 1 by LA plus 1 by LS. So, these are some of the relationships which will help us to know what is the amount of absorption that is taking place in the medium, absorption or scattering, total losses taking place within a medium. So, this is like a schematic representation of attenuation, like some medium is present here. When EMR passes through a medium, its amplitude will be going down, and finally it may also be totally absorbed within the medium. So, its amplitude will be reducing and hence its total energy content will be reducing. Just two more properties of EMR, find some obstacles on its path. Rather than being completely stopped by the obstacle, EMR has the property of bending around the edges of the obstacle. Like in our school physics labs, we might have done experiments with prism where we try to split white light into its 7 different colors. So, that is the thing, that is called like diffraction by a prism, like how light ray is bent around the edges of some obstacles within there. So, lens, whenever like it encounters a lens, around the lens border it will be like bending at some angles. The angle at which the light ray is bent depends on the medium and also on the wavelength. Similarly, when there is a relative motion between the source and the observer, like source and the observer, like some EMR source is there, some observer is there observing this particular EMR. When these two things, when the source and observer are moving towards each other or moving away from each other, there will be an apparent shift in the wavelength of the EMR as observed by the observer. This is known as Doppler effect. Like Doppler effect we might have heard in sound, like there will be a change in frequency of the sound. We should have studied this in school. EMR also will undergo such Doppler effect. This kind of Doppler effect is used in mostly like in astronomy to study about stars, because like earth is in continuous motion, stars are also in motion. Due to this relative motion between the source and the observer, the wavelength observed by the observer will be different from what is originally coming in. But different means the wavelength will not change actually, the observer will perceive as it is, that is why we call it as an apparent change. there will be like an apparent change. Okay. So, maybe just few important points I have given here. So, when the source and observer are moving towards each other, wavelength will shift towards shorter end. Shorter end means it will become a shorter wavelength. Say for example, like some object is emitting like red light and that particular object is moving towards the observer, then if it is moving towards, observer may perceive that particular object in a different color with shorter wavelength, maybe green or blue or whatever, depends on the relative velocity between them. But this is only apparent, it is not the actual change. So, with this we complete the lecture on the basic introduction to the properties of EMR. In the properties of EMR we studied about polarization, coherency, and also we studied about reflection, refraction, and what sort of losses will occur like scattering and absorption. All the things I introduced to you very briefly just for you to understand deeply when we talk about them more in detail in the coming lectures. Thank you very much.